So what we're going to show is that in principle investment problems should be more difficult than prediction problems, as I just discussed. Okay. And the following result we're going to show is that actually in some sense they're the same level of difficulty, at least for the case of these constantly rebalanced portfolios. That's where each unit of time you're keeping a fixed proportion of your wealth, okay, in the different assets. Okay, so you're going to consider how well a policy you can construct relative to those sorts of settings, those sorts of constantly rebalanced portfolios. Okay, so the theorem we're going to prove is that for a set of constantly rebalanced portfolios, okay, and if we consider the prediction strategies P induced by I, so we just look at what those fixed proportions of investments mean in terms of the horse racing example. So particularly you're going to try and, in those cases, you're going to look at kind of a fixed investment in those horse races each unit of time. We're going to have the wealth factor of the investment strategies are equal to the wealth factor of the horse racing example. Okay? Moreover, in this case, the minimax optimal investment strategy, okay, so we take the minimax optimal investment strategy is the investment strategy that is induced by the normalized maximum likelihood prediction policy. Okay? So we take our normalized maximum likelihood prediction, use it to construct an investment strategy, and that is going to give us the optimal wealth factor for an investment problem. Okay? So that's what that's saying. Okay? And the first thing we can show is that the regret we get from investment is higher than the regret we're going to get from prediction. Okay? So that, in some sense, this result doesn't hold just in the context of this theorem, but it's showing that actually that the regret being bigger means this problem is definitely harder than this problem. Okay, so investment is harder than prediction. Okay, so that's interpretation of the first thing we'll prove, and then we're going to work a bit within the framework of constantly rebalanced portfolios to prove that the inequality holds the other way around as well. Okay. Okay. So let's go about showing that. Okay. So the answer for this guy is that, let's just look at the definition of the wealth factor. Okay. It is, we can write it a little bit more compactly as follows. It's the worst case regret that we can get over the sets of histories up until time t, and then it's given by the worst case policy, or the best policy subject to that. And I could make this into a maximum essentially by switching the order in the logarithms in here. Okay? 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 Okay. And then what I can notice is I can sequentially make this guy a bit smaller each time by replacing this maximum with the maximum over Kelly market vectors. Okay, so let's have this as a maximum over Kelly market vectors. Okay. That's only going to make it smaller because the sets of histories set of histories has the Kelly market vectors as a subset. Okay? So maximising more stuff than we are here. Okay. 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 All right. Okay. Then notice that the wealth factor of a policy with respect to Kelly market vectors is just the product of the policies pi, and I'll explain why that is in just a second. But one of the things I can notice is this is going to be exactly the same as the maximum here, maximum over pi of I over pi tilde of h of t divided by pi. Okay? And I'm kind of realizing really I should have a minimum over pi tilde here if I'm going to be completely rigorous. But anyway, because pi tilde is going to come out of nowhere, there should be minimum pi tilde here and then minimum pi tilde here. Okay. I'll leave it like that for now. Okay. I'll explain why that is true in a second. Okay. And the thing to notice about that is this is exactly the definition of the regret of a policy P with respect to a set of prediction policies, capital P here. Okay? Because I could think of this, instead of being a maximum over pi, I could replace this with a maximum over the sets of policies P which were induced by pi. Okay? So if I let that be the induced policy, let me just get a colour here. So here I'm saying that this P is the policy induced by this pi tilde. Okay? Right. And then finally, if I minimise this over the sets of policies P, then I'm going to end up with V of T of P. Okay? Alright. And really I should have some sort of pi tilde over here. I'll write like a pi tilde there to make it a bit more rigorous. And then if I minimise this over the pi tildes, I'm going to end up with So the one thing to mention about why is the wealth factor here equal to that, that's the one thing I didn't really cover properly. So you notice that, so why could I go from here to here? Well, if I just write down, so I'll just make a kind of margin note here. I'll change colour as well so we can discuss. So why does that go to that? Well, it's because the wealth factor of, say, policy pi with respect to the Kelly market vector history, H, okay, notice that's really, by definition, that's the product from time equals 1 to t of S of t of H of t pi of H of t given the history up until that point, which is the Kelly market vector. Okay? And so I've got a product of two things. I've just got a product over the sets of stock increases and a product of the policy pi. Okay? So I'm going to end up with this guy times all by pi h of capital T. Okay, so that product applied to this is going to give me that, and then this is the rest of the product left over. So when I consider the wealth factor of pi divided by, the wealth factor of pi tilde divided by the wealth factor of pi, the terms to do with the stocks are going to cancel out. Okay, so that, if I put that product of S of t in here, it's going to cancel with the one at the bottom, and I'm just going to be left with pi tilde and the pi here. Okay. All right, so it looks a bit fiddly, but at the end of the day, the only thing that really matters is that because the sets of market vectors is much bigger than the sets of Kelly market vectors, or the sets of things that can happen in horse races, then it has to be that this is bigger than that. At the end of the day, that's the main thing. Okay? And there's a lot of maximums and minimums stuck in there just because we've got definitions with lots of maximums and minimums. But that's essentially it. Okay? Now, we're going to work to try and prove the result in the other direction. We want to prove that they're equal to one another. Notice this argument is basically going to hold for any policy. We want to prove that the opposite direction. Okay? And in order to do that, we're going to need one technical lemma, which is the following. Oh, I've even got the proof ready for you as well, for some reason. Okay, seem to have forgotten to delete that, but it doesn't matter. Okay. So show that for any set of non-negative numbers, a1 up to at, and b1 up to bt, that if I sum up the a's and I sum up the b's, that's less than the maximum of the a divided by b. Okay? It's just some fiddly lemma that you could prove in your analysis class. We could ask this to whoever we like. Okay? So essentially, one way of proving this is to notice that the sum of the a's divided by the sum of the b's, we could divide by b here and look at it as a weighted sum. Okay, so I could think of the weights being the ratio of bt divided by its sum of these at divided by bt. Does everyone agree with that? Okay, so just times and divided by bt here. Okay. And then, and I'm probably thinking I should probably say not even non-negative, I should probably say positive here. Anyway, then I could just, well, I'm certainly going to make things bigger if I take the biggest of these at divided by bt's. Okay? So I'm looking kind of a weighted average of these terms, and I just take the biggest term possible. That's going to give me that. And I need an inequality here. Apologies. It's what happens when you write notes for the first time. Okay, that way. Okay. And then I've just got an average of something that's constant, so it's just going to give me the term that I want. Okay. So that's just some technical lemma. Doesn't really matter. It's just something that's going to be useful for us. Okay. Right. Okay, next thing. So what we're going to try to do is look for kind of nice expressions for the wealth factor. Okay? So one thing we're going to show is that the wealth factor of any investment policy can be expressed as a sum over Kelly market vectors. Okay? So this isn't actually too bad. But notice, okay, so the definition of the wealth factor is just the product, okay, from t equals 1 to t, of the increases of the wealths of the investments in each stock. Okay. Now remember, I can write that out as a sum, just like before. I can write this out as a sum of the first stock times the proportion of wealth in the first stock plus the second stock and the proportion of wealth in the second stock And I'm going to write it in that slightly strange way with these h of t's. Okay, so I'd have like 1, 0, 0, 0, 0 would mean the first stock, 0, 1, 0, 0, 0, 0 would mean the second stock, 0, 0, 1, 0, 0, 0 would mean the third stock, and so forth. Okay? Alright, so now, one way to think about this is I've got a product of some sums. So I've got like A plus B, and then I've got a product here for the next time. I've got C plus a D. Okay, and I could think of that being like 0, 1, 0, or I could just have 0, and I could think of that as being 1. Okay, and I could think of that being 0 and that being 1. Okay, so when I expand this out, I can look at it as like I put the zeros together and multiply them, and then I get the 0 and the 1, I put it together, and I get the 1 and the 0, put it together, and I get the 1 and the 1, and put it together. Yeah? So I could look at that as like 0, 0, 0, 1, 1, 0, 1, 1. Yeah? Does everyone agree with that? And then for the 0, 0, I got A, C, 0, 1, I have A, D. Okay, I have 1, 0, B, C, and then finally 1, 1 is B, D. Yeah? Okay, so one way to think of it is something to do with a sum with 0, 1 vectors. Another way to think of it is like all the combinations of the 0, 1 vectors. Okay? So in other words, notice here I've essentially changed the order, so it's a sum with a product. It's like a product with a sum. Okay? So in other words, what I'm saying to you is I could look at the history up until time t, and then do the product inside. Okay? Okay? Of the components of the history. Okay? So the trick there is rather than having like a 0 and a 1, I've changed it to the format where it's like a vector of 0s and 1s. Okay? And that's the general trick for, when you can change a product and a sum. Okay? Which is exactly what I wanted. Okay? Alright. So just sort of expand the brackets essentially, but it's, with a bit of tracking. Okay. Next thing. Show that for pi, the investment strategy induced by the normalized maximum likelihood policy, we have the following bound. Okay? This is kind of the crunch lemma, or result. Okay? It's sort of showing that we kind of chuck away all of the stock information and we're just looking at the performance of our policy relative to the predicted performance of each sort of expert or investment strategy that we've been given. Okay. And one of the things, this result isn't for constantly rebalanced portfolios. Okay. So I've got this conditional on the history up to this point. Okay. But the nice thing that will happen is if we assume that P is a constantly rebalanced portfolio here, with the past history doesn't matter anymore because we're just constantly rebalancing. Okay, so once that's gone away, we're just going to have something that's like the prediction policy's prediction of the history compared with our prediction policy, prediction of the whole vector of the history. Okay, all right. So this is kind of the hardest step. Okay. So, if I look at the and the way I've kind of looked at it here is looking at the exponential of this guy because I'm a bit fed up of all the logarithms and all the rest of it. So when I first wrote out the proofs, there's logarithms everywhere. I try to get rid of them. So the exponential of the maximum of the regret over the past histories. Okay. Well, by definition, okay, this is just the definition of the regret. It's just the max over the sets of investments, the wealth factor of those, relative to our policy. Okay, that makes sense. It's just sort of like, okay. So now I'm going to use the definitions from before. Okay. So in both cases, I can write these things out as a product. Okay, as a sum over the past histories. Okay. So here I have this is equal to the product over the histories. The sum over the histories, product from t equals 1 to h of t, p of t of h of t given h of t minus 1. Okay. Okay. This is exactly just the exercise that we just proved. Okay. So this is by this is by 153. This first part. Okay. And then we can divide it by the sum of the histories until t plus 1 pi of t of h of t product of tau equals 1 to t s of tau of h of tau. And that one, we're using the calculation we did before where we showed that the wealth factor of an induced policy was given by that f of t plus 1 term. Okay, because we've assumed this is an induced policy. So here to here is, I'll just get the number of the exercise, but it's the one where we looked at these f of t's. This one is number 150. Okay. Okay. Right. Then what we've got is the sum over all the histories, and sorry, I should get rid of that t plus 1. Oh, get rid of the t plus 1. So I've got a sum over all the histories up until time t of Cayley market vectors. Okay. And now I'm just going to use the lemma that we proved previously, that if we've got a sum of a bunch of a's divided by a sum with a bunch of b's, it's less than or equal to the max ratio between these two. Alright? So using our lemma now, that this is less than, oh, and I should have keep this max over p here, apologies, I'll just keep that max over p alive. Max over p, and then the biggest term of these two over the histories, max over h of t. Okay, and notice when I do that, since these s's are going to be matched up together, the terms to do with the stock increases are going to cancel out. I'm just going to be left with p of t of h of t given the history up until time t divided by pi of t of t of h of t, and then I need a product in there, sorry, product t equals 1 until capital T. Okay, let me just space that out a little bit better for you. And I'll make that a bit bigger. Okay. That right. Okay. Which is what we wanted. It's this expression here. Okay. So the final inequality there was that lemma we just proved. So I think that's 152. I'm right. So they're using 152 there. Right. Okay. Right. That's the hardest bit today. So now we just need to kind of collect things together a little bit. Okay. So we have basically what's quite a nice bound that says that we've managed to get rid of all the information that cares about the stock increases, okay, in this inequality. We've said the regret of an investment policy here, given a past set of histories, is bounded above by something that doesn't care about the stock increases, and all of the terms here, okay, they're in this maximum and all the rest of it, are only to do with the prediction of stocks, okay? So we've got rid of, except for this script h of t, we've got rid of everything that's to do with stock price histories, and we've replaced it with something that's to do with horse racing predictions, okay? So in particular, what we're going to show here is that if for I, a set of constantly rebalanced portfolios, and for pi star, the normalized maximum likelihood policy for I, okay, we have the following bound, that this term over here is less than or equal to the minimax regret of the prediction. Okay? Okay, so let's do that. So we're just going to use our bound from the previous exercise, okay? So from the last exercise, we have that max regret over the sets of histories is less than this. Okay, so for the sets of policies in I guess now, max over the histories, okay, and then the logarithm of our investment policy pi star, okay, divided by, well, notice when I consider a constantly rebalanced portfolio, okay, or the set of all constantly rebalanced portfolios, each of those individual strategies doesn't use the past history when it's making its decision, okay? There might be a best one amongst it, and that might be dependent on what the history was, but the actual policies themselves don't use this history, okay? So notice, what I'm going to end up with here is just P of T of H of T, because P of T of H of T given H of T minus 1 is really just P of T of H given capital T of H, or is just doesn't really matter about the past, it just uses the current information, okay? So we don't have this bit, so we just end up with the product, okay? Right, okay, so nearly there. And then finally, now we've got something to do with the prediction policy, and remember that the maximum likelihood forecaster, okay, is the one that takes the maximum over all of these policies here and then sums up and renormalizes. Okay, so notice I can just put this maximum, I can put this maximum inside here, and I've got the max over the sets of histories log of the max P in I, P of t, H of t, divided by pi star of t, H of t. Okay? Now, remember the way that we wrote the maximum likelihood, normalized maximum likelihood forecaster is exactly the probability is proportional to that, isn't it? So remember, is by definition the max over P of t, H of t divided by the sum of all the histories max over P of t, H of t. Let me make that a bit bigger again as well. Let's get that better as well. Okay, H dash of t max over P okay, that's just the definition of the normalized maximum likelihood forecaster. Okay, so you can check that this is just going to give us, this is just going to be equal to the normalizing constant for each of these guys. Sorry. So in this case it's this sum over H dash of t max over P, pt over H dash of t. Okay, and so we're using the definition here. That just follows from the definition of the maximum normalized maximum likelihood policy pi star. Okay, and then finally we showed just going to jump back. So we've got this sum, the normalizing constant of this maximum normalized likelihood forecast. I'm just going to skip back briefly. We can remember that we showed at the very end where we're considering the horse racing example. Okay. So first we showed that if we considered P star, the prediction strategy of the normalized maximum likelihood forecast, it was exactly this sum. Okay? Which is exactly the normalizing constant here that I use for the normalized maximum likelihood forecaster. Okay? So in other words, that is exactly, just getting back to where we were, is exactly this. Okay? So this is exactly VTP. Okay? And then finally, the thing to show is that the theorem holds, okay, which we've basically done at this point. Okay, we showed that the regret of one policy, okay, is less than V of T of P, and W T of I is the minimum overall policy, so it must be true. Okay, so notice that. So just to finish up, the wealth factor from I is the minimum overall policies, okay, of the max regret over all the histories, which obviously is going to be less than, oops, sorry, let me remove that star, which is going to be less than this minimum. If I choose one specific policy, it's only going to make things bigger. So if I put in pi star, it's only going to make this bigger. Okay. And then, for my last exercise, 55, we have that this is bigger this is less than V of t of p. Okay? So we know that that's saying that the investment problem is easier than the prediction problem. And we know that this is also greater than V of t of p from our previous exercise. So let me just get the number there. I'll let you copy down and I'll get the number. I probably have it here on this sheet of paper. So we showed that that was true in let me get it here. Exercise 151, yeah, thanks. 151. Okay, and that's it. Okay. All right, so after this, probably don't really have time to cover it, but so that there are then things about how there's a lot of maximizations and summations going on in the normalized maximum likelihood forecaster. Okay, so what's been done in practice is replacing that by some sort of approximation. Okay, and the results that you can prove about something where you place like a Bayesian prior instead of having that summation, and then there's something called a universal portfolio. Okay, universal portfolios like an approximation of the normalized maximum likelihood forecaster that was been used in hedge funds in the past for essentially balancing portfolios. Okay, and you can prove that although it's not got the optimal performance like the Minimax one, you can prove that it's within certain factors, the logarithmic factors and so forth of the